Thank you for the introduction. Today I will talk about SRAM-based in-memory computing for energy-efficient AI systems. It's a pleasure to be one of the speakers at this e-TEC talks at SNU Summer 2021. So as we know, there has been a lot of success in AI algorithms that have been applied to many different systems, including healthcare, smart home, agriculture, self-driving, and so on. And boosted by these, there has been a lot of custom chip designs for AI. As you can see, there has been a lot from major industry players. A number of new startups nowadays are on the scene. And of course, academia research is also prototyping a lot of chip designs for high energy efficiency. And many more will come. So if we look into some of these AI inference accelerators, we can see that the data movement actually is a key bottleneck. So we know that there's a lot of operations and computations that need to be done for AI. However, to actually do the computation, we have to bring the data to where the computation happens. And if you look at this plot from ICC 2021, you can see that the y-axis is showing the energy per access per 64-bit word. And you can see that compared to like any 4-bit, 16-bit, or even floating point multiplier to get to a larger memory and going to octave DRAM, and this is in the log scale, is consuming an exponential high amount of energy. So you can see that the data movement and communication costs can easily dominate the overall energy and throughput. And this can be seen also in some of the literature, all digital AI hardware. And you can see from this Iris, this work from KAIST, and this recent chip from NVIDIA. And you can see that if you look into this power and energy breakdown, a large portion, maybe more than 2/3, have been consumed by these scratch pads, these banks, weight banks. These are all SRAM, and accumulation buffer, and input activation buffer. So including all these and the router, basically to access the memory, access the data from on-chip memory, and then to get that data to where the actual computation happens is actually dominating the overall power and energy. So given that bottleneck, if we look into the conventional illustration of the conventional all-digital implementation, that bottleneck is happening because, let's say, data is stored in on-chip memory. These can be different memory technologies. And then typically row by row with a limited bandwidth, we bring that to an on-chip buffer. And then we have to bring that to a separate physically located compute engine, like a systolic 2D MAC array. Now, this has this latency and data communication overhead. So what has been emerged in recent years is so-called in-memory computing, which is a different computing paradigm where we turn on multiple or even all rows of the subarray and actually do the multiply and accumulate operation, which is the dominant operation in many AI algorithms inside the memory in a mixed signal and analog manner. So because we are not bounded by the row by row and we can turn on all the rows simultaneously, we are maximizing the parallelism, and then we don't have to bring the data to a separate MAC engine, and we're actually just doing the MAC inside here, and then the partial sum, the MAC result, just can be outside. So there's a large reduction in data transfer, all contributing to high energy efficiency. But some of the key challenges are we're now basically going from a high noise margin digital computation to a mixed signal analog computation, which exhibits variability, and that might result in some DNN accuracy degradation. So in terms of in-memory computing, we're trying to basically do computing inside the memory. And then we know that there are different memory technologies. And for these different memory technologies, in-memory or near-memory processing has all been explored and investigated, and more will come. But in a high level, there could be SRAM, there could be DRAM, and there could be other non-volatile memories, such as resistive RAM or phase change memory. I quickly summarize the advantages and challenges of each of these memory technologies. So you can see on the SRAM, the main advantage is that SRAM is going to be in any latest CMOS technology, whether that's 5 nanometer 2 nanometer and so on. Comparing the on current and off current, the ratio is really high compared to some of these non-volatile counterparts. And then it's reliable. We know how to fabricate them in a large scale. So large scale integration is not really a concern. Some of the challenges are we're not, in-memory computing, we're not really using the off-the-shelf 60 SRAMs anymore. So the push rule that the foundries have rigorously optimized cannot be used, and we have to basically make a custom bit cell, a new push rule for that, which means that a lot of manpower has to be involved, and additional transistors and components results in higher area, while the area per bit is always a concern for SRAM. Because the area is a concern, DRAM can be thought through, and DRAM energy, communication energy is the highest. So obviously, if we can do a lot of computation in the DRAM chip, that will significantly reduce the DRAM access energy. However, the main challenge is that the DRAM cell is 1T, 1C typically, which is destructive when we read out the value, which means that to do real in-memory computing in the DRAM, we have to modify the bit cell and the array possibly, but these are very difficult because the DRAM fabrication process is strictly governed by the players such as Samsung and SK Hynix. On the other hand, driven by the density benefits that are more dense than DRAM, RM and PCM types of non-volatile memory has been heavily investigated nowadays, but some of the known challenges are compared to SRAM, the on-off ratio is relatively low, could be less than 10, and these are not necessarily offered in all of the CMOS nodes, and still compared to SRAM, large-scale integration is a problem. And even though the bit cell might be smaller, the peripheral circuits doesn't necessarily scale accordingly. So the overall area, whether how much density improvement we get, is something we need to certainly check. So driven by these advantages here in this talk, we'll focus on the SRAM-based IMC design, since it is most robust and viable for large-scale integration in any CMOS technologies. So let's first go through some basics of the analog in-memory computing, and let's first look into a single SRAM column, because we're assuming that we're going to turn on multiple or all rows of a given SRAM array, and then we're doing multiply and accumulation along the column with many of these inputs coming in. So in a sense, typically the weights are stored inside the SRAM, and which the basic one is the 6T, and then in AI algorithms, we have a lot of multiply and accumulate between the activations and weights. So the activations are typically applied on the word line. And the initial work started from just using the off-the-shelf 60-bit cell, just turning on all at the same time. There are some read disturb issues, but this can use the off-the-shelf SRAMs with high density. But because of the read disturb issues, for better stability, people came up with some different schemes, and that includes, we still use the 60-bit cell, but we add some local analog computation modules that are shared between a small group of 60-bit cells, such as 16, for example, and we can have 16 of these for like a 256 row SRAM. So this adds relatively small area overhead, but within the group, still only one SRAM is accessed, and this is a row by row, so the parallelism is not maximized. Now, there have been also a lot of approaches where we just add a couple or extra transistors and create a new bit cell that is very efficient for analog and memory computing. And then the activations are applied on the read word line, for example, on this extra transistor part. And then each of these bit cell computes an element-wise multiplication between activation and weight. And then when we combine or connect this RBL from all the cells together, we're basically accumulating these individual multiplications, computing the sigma of the individual A multiplied by W. So this adds area of coupled transistors per bit cell. So among these three, it has the highest area overhead. However, the parallelism is maximized because we can turn all the rows, resulting in highest throughput and better energy efficiency. Now, in terms of the analog SRAM IMC, there can be two categories largely that I categorize as resistive and capacitive. In resistive IMC, I kind of put together two representative works here. So this is the work from TSMC and SSMC 2020. So you can see that they're basically doing an AND function within the bit cell. So only when the word line is high and when the storage node here has a high value, then we're going to pull down the bit line. Otherwise, all of these other cases, we're not going to pull down the bit line. This is our work called XNOR SRAM, and the key computing mechanism here is that the RBL is there, and then we're doing an XNOR operation between the inputs and the weights, where inputs and weights are either represented as +1 or -1. So the key computing scheme here is that whether it's +1 +1 or -1 -1, we need to pull up the RBL, as you can see here. And when it's -1 +1 or +1 -1, we need to pull down the RBLs. So in the same column, depending on, and now, when we turn on N cells in an SRAM column that connect to the same RBL, in this TSMC work, you can see that proportional to how many of the cells pull down the BL, we can see that the RBL will have a monotonic relationship between the number of bit cells that pull down. And in this XNOR SRAM scheme, we'll have a resistive divider between the bit cells that pull up and bit cells that pull down. So this becomes a more resistive divider. This becomes a time-dependent one. And this will have some crowbar current between VDD and ground, depending on the number of cells that are pulling down and pulling up. Now, when we turn on N rows, we're basically performing an N input dot product or MAC in a single cycle. And depending on the power, the cells that are pulling up versus down, as I said, we're going to have a monotonic relationship between the mathematical MAC result, as you see here in the x-axis, and the RBL voltage here, as you can see here. In the capacitive SRAM INC scheme, I also put together two representative works. This work is from Levine Vermeer's group in Princeton, where they use these PMOS transistors as additional access transistors, and they store the multiplication result between the input activation and the weight stored in the 60 SRAM into this capacitor. Either they charge up to VDD or dissipate the charge to ground. And then in this other work from ours called C3 SRAM, we use capacitive coupling. So we have two NMOS transistors here, and from the middle node, we capacitively couple the individual multiplication result to the multiplication bit line or MAC bit line or MBL. Now, in these capacitive schemes, when we turn on N cells or N rows together, in this Princeton work, they're basically doing charge sharing. So after they discharge or charge each of the capacitors to VDD or ground, when they turn on all of these together, they're going to settle down to some analog voltage value in the middle, and that will represent the MAC. And in the capacitive coupling approach, we're essentially implementing a capacitive divider. Some of the cells will pull up the capacitor towards VDD, some of the cells will pull it down to ground, and depending on the cells that are pulling up versus pulling down, MBL is going to result in an intermediate voltage. And you can see that compared to the resistive approach that is basically driven by transistors, the nonlinearity has driven that the transfer function is not really a straight line. But in the capacitive approaches, you can see that it's much more of a straight line after some calibration, and due to the NMOS transistor passgate, the pull up, transferring the VDD results in some VTH drop, but still we have a relatively linear relationship between the MAC value and the read bit line voltage, as you can see here. I want to mention that in these in-memory computings, we're getting these analog read bit line values, as you saw here, and also in the resistive approach, and these have to be digitized so that the ensuing stage can use the digital values to do the next stage or next layer computation. And this ADC design is actually an integral part for a lot of these IMC works. So I just want to mention some optimizations that we did. For example, the ADC precision, or in this work, we use flash ADCs. So the number of ADC levels doesn't have to be a power of 2. So that's why we swept this fine grain. And depending on the network, in this case, we benchmark some networks for CFAR10 data set. And obviously, we don't want to lose a lot of accuracy. We want to match the baseline accuracy as much as possible. So we can see that as we increase the ADC precision, at some point, the accuracy will saturate, and these points were selected as design point. Obviously, if we use too low precision, then the ADC design will be simpler, but we're going to lose a lot of accuracy. And also, specific to IMC, some of the things have been optimized separately. For example, typically in an ADC design, you have an input and minimum and maximum value range, and you typically divide that linearly throughout the whole range. But in the neural network case, we actually benchmark some MLP, and from the entire maximum to minimum value, we noticed that when we do the MAC, the XNOR and accumulate, the value is actually highly concentrated in the middle. So if we do the linear quantization with the ADC, these values won't be really of much of use. So there can be two things that we can do. We can do nonlinear quantization, where we just put the reference levels close to each other where the data is the highest. And when there's scarce data, we won't really put any reference levels. And you can see that will be most dense here, and then it kind of spreads out as we go to the right or left. On the other hand, we can do clip linear quantization. So we can put a clip range, and within that range, we can do linear quantization. Now, this AD design also is going to be heavily dependent on the in-memory computing scheme, and this is our XNOR SRAM design. And because it has been driven by pull-up transistors and pull-down transistors, we have this steep region in the middle, nonlinear region in the middle, and we're using a flash ADC. So in this nonlinear quantization, what we actually notice is that the highest amount of data is here, but that's where actually the reference level delta is the smallest between adjacent flash ADC reference voltages, and that makes it subjective to the non-zero offset that the flash ADC has. On the other hand, when we use clip linear quantization, where the data density is the highest, we're actually spreading out the delta references between adjacent reference levels of the flash ADC. So due to that, actually, for the same network, when we use this linear with a clip range compared to a nonlinear, we got several percent of accuracy improvement when we benchmark the same hardware for different AI algorithms. Now, just wanted to quickly summarize the two macro level IMC prototype works that my group and actually Professor Mingu Saku did just the previous presentation at Columbia University collaborated on. And the first one was the resistive IMC called XNOR SRAM, and the capacitive IMC was called C3 SRAM. Both have been presented at published at JSAC 2020. And the XNOR SRAM achieved 400 tops per watt, and the capacitive IMC achieved 622 tops per watt with relatively high accuracies for the CFAR10 data set. So these were the good resistive and capacitive IMC SRAM macros that we prototyped. But recently we went in several directions beyond a single macro design illustrated here. So we had these two different single macro design, but obviously the neural network is very large, while each of these prototypes only has a 256 by 64 custom in-memory computing SRAM array with accompanying peripheral circuits. So one direction is that obviously for a large-scale accelerator, AI accelerator that can do a whole network on chip, we will need to instantiate and integrate a large number of macros. So recently we published a 108 macro integrated programmable accelerator and presented at Symposium Villa in June. In another work, we noticed that there are a lot of design parameters that we need to optimize in IMC design, and we put together a modeling framework to optimize all of these different design parameters, and given different noise, we want to understand how much accuracy will be degraded. And given the noise of these IMC schemes, inevitably, if the noise is high, there will be some accuracy degradation. We put together a custom training algorithm that can improve the DNN accuracy. And finally, there has been a lot of concern also on adversarial attacks and robustness of AI. And we try to, on the other end, exploit some of these inherent hardware IMC noise towards adversarial robustness. So I will devote a lot of the time, the rest of the time on this programmable accelerator. And then for the three other works, I will quickly go over them. So this work called PIMCA was a collaboration with Columbia and Samsung Advanced Institute of Technology in Korea. And we put together a 3.4 megabit programmable IMC accelerator in 2028 nanometer. So there has been a lot of single macro designs starting from 3-4 years ago. And recently, obviously, a lot of research groups are also marching towards an IMC system. So just quickly summarizing some of the IMC macro and system designs, on the left, you can see that there has been a number of prototypes from MIT. I already mentioned this X1 SRAM and C3 SRAM for our group, and National Tsinghua University and TSMC. And these macro sizes are relatively similar, something from 64 to 56 in the row and column dimension. And putting together a number of these into a larger system, you can see that different groups integrated as small as 4 macros, 16 macros, up to hundreds of macros that we did. And these has been published in recent conferences or journals. And I will go into some further details of our PIMCA chip that we integrate, where we integrated 108 macros of a 56 by 128 IMC macro design. So first, there has been some prior works on IMC systems, but this slide is just pointing out to some key limitations. First of all, as I showed in the previous slide, there has been some IMC argued systems, but their integration capacity was not that much, only like 16 kilobits and only 4 to 16 macros. So they added some sparsity awareness, but limited amount of parallelism can be exploited, and the non-Mac operation support was non-existent, for example, in this ISCC 2020 work. In this other Princeton work from GAC 2020, they put together a programmable IMC array together with the open source RISC-V processor. The IMC SRAM capacity was 576 kilobit, but other scalar operations such as pooling, residual addition that is necessary for ResNet type of networks were not supported. So the motivation of our proposed PIMCA chip, which stands for Programmable In-Memory Computing Accelerator, is that we wanted to propose and put together a programmable IMC architecture with custom instruction sets. And also we wanted specific control and support on hardware loop, which exists a lot in convolutional neural networks and different types of deep neural networks. So we wanted to reduce the number of custom instructions for iterative and repetitive DNN workloads. And obviously the same chip should try to support many different types of networks, and exploiting some of the recent ML algorithms on very low precision quantization. We support the 1-bit and 2-bit activation and weight precisions for these different networks. And we integrated 108 IMC SRAM macros, demonstrating one of the largest integrations for IMC systems to date. And this means that for edge devices, medium-sized DNNs can fully fit on chip. So this is the overall PIMCA architecture. As I said, we're putting together 108 IMC macros, where one macro has 256 rows and 128 columns. And 108 IMC macros are divided into 6 clusters, 6 PE clusters, and one PE cluster has 18 IMC macros, and different macros, different PE clusters can communicate to the 256-way SIMD engine, which will take care of different non-Mac operations. And we have a separate activation memory with off-the-shelf SRAMs with an amount of 1.5 megabit. And we have some instruction memory, different loop support, and other modules that enable the chip operation. And the SRAM cell is a 10T1C SRAM cell that is an extension of the C3 SRAM that I presented previously. The change is that there has been some VTH drop on the NMOS passgate, and we complemented that with the transmission gate here so that it has better swing from 0 to VDD. And we have a 4-bit flash ADC output for every column. So each 256 by 128 IMC SRAM array can do a full vector matrix multiplication in one cycle, and then this flash ADC will get the 4-bit output accordingly. We have a separate activation memory of 1.5 megabit, as I said, and this processing engine, the P cluster and the SIMD are pipelined. I will show you a pipeline diagram in the next slide. And the top controller fetches and decodes instructions from the instruction memory every cycle and controls how the IMC and SIMD need to do the necessary computations. So this is the IMC plus SIMD pipeline in our PIMCA chip. So we have this instruction fetch, instruction decode, load, the input activation, IMC, in-memory computing cycle, the SIMD cycle, and then the write back. This is the 6-stage pipeline. The activation memory is organized, as you can see, in 2 groups, the top and bottom. Each of these activation memories are off-the-shelf single port 60 SRAM. So this pretty much does the double buffering. When one group is used for reading, the other is used for writing new values into it, being ready for the next stage. And this PE, please note that this is bypassable in case that we just need to do some SIMD data without necessarily always going through the PE for IMC. So these are the instruction fields. We have different loop operations, the activation memory access, the IMC related part, and SIMD related part. So the total instruction width is 72-bit, and the regular PE plus SIMD instruction configures the data location for read and write, the IMC PE operation mode, and different SIMD instructions. As I said, one particular emphasis that we put together in this PIMCA chip is the loop support control. So as I illustrated in this for loop of a given CNN algorithm for a 2D convolutional layer, there are many different loops that has to be iteratively computed for this high dimensional input MAC computation. So we know that there are a lot of loops and repetitive and iterative computations for DNN inference, and we try to exploit this to reduce the size of instructions instead of having a MAC or P instruction for every single MAC operation, for example. So there are 2 types of loop support that we put together in this PIMCA top controller. The first one is simply repeating a single instruction for RP times. So we can just put this 6-bit field for RP, and this just designates how many times it has to be repeated for the current instruction. This can address, for example, automatically increasing the address in each repetition. The second one is the generic nested loop, as I showed you 2 slides earlier. And this can be defined by special loop instructions with dedicated counters and registers, as you can see here. And these were some examples of the loop instructions with different arguments. By exploiting these A and B type of 2 types of loop support for BGG9 network that we benchmarked for CFAR10 dataset, we found out that the number of total instructions has been reduced by 4x compared to the case where we didn't apply any loop support. So this largely reduces the necessary storage for the instruction memory and also simplifies the overall operation. So now I'll show you some PE. So again, the PE is the cluster that integrates 18 IMC SRAM macros, and I'll show you several different mapping examples that our PE cluster can support. So with 18 IMC SRAM macros, these are divided into 9 on the left and 9 on the right, as you can see here. Given that 3x3 convolution kernels are still the predominant size of kernels in CNNs, this can naturally efficiently support 3x3 kernels happening at the same time. And I told you that we can support either 1-bit or 2-bit precision for both activations and waits. So we can either do a 1-bit 256 input channel, 256 output channel, 3x3 convolution kernel with this 18 SRAM macros, or if the bit precision is configured as 2-bit, we can store the MSB of the 2-bit weights on the left 9 macros and LSB of the 2-bit weights on the right macro, do the individual computation, and then these can be combined later. And you can see that this pink block is not just a single flip-flop, but these include some separate shift register for the MSB and LSB of the 2-bit input, and this supports the bit serial scheme for the 2-bit input precision CNNs. And in another mode, the PE can be mapped to support a fully connected layer. This 18 macro can support up to, let's say, 2300 by 256 fully connected layer MAC operation in one shot in a single cycle. And the output of that, the accumulated value, will be delivered to the SIMD ensuing. In the other mode, the PE can be also mapped to support 5x5 convolutions. There will be some extra IMC that are not needed for this 5x5. So in those cases, we disable it and set the output to be 0 automatically. And you can see that we enable these 5x5. There are some inactive rows here at the most bottom SRAM IMC. So we just make the eventual output to be 0 by having half of them +1 and half of them -1. But this can support basically 5x5 by 128 channels, input channels, and 128 output channel convolution in a given layer. And finally, this slide shows the peeing mapping example about different paddings that are needed for kernels. So sometimes you need to pad 0 for full or fine convolution. And in some cases, in conventional designs, you had to pad those zeros in the activation SRAM activation buffer, so that those zeros have to be transferred to where the computation actually happens. But in our case, we don't need to do any explicit zero padding on the input feature map themselves, because instead we try to negate the computation happening and mask this the IMC macros don't need to be happening for considering the zero padding, so that we don't need to change anything in the input feature map. These will naturally just take care of the zero padding operations. And with these are showing some pin cut chip mapping. So, in the previous slide, this was showing 1 PE of 18 SRAM macros. So this block shows 1 PE, and as I said, we have 6 PEs for a total of 108 macros. So this slightly customized 9-layer VGG with about 3 million weights, and the binary mode can get fully mapped on the pin cut chip. And this shows different layers. And typically, as we go to deeper layers, the size of the width of the layers go up. So you can see that how the different layers get mapped to the pin cut chip, as you can see. And then for different networks, for example, Resident 18 that has much more weights, like 11 million weights. And obviously, this cannot be fully implemented in a 3.4 megabit pin cut chip. So which means that we'll have to go through some time multiplexing 4 times to go through all of the layers, as you can see. And this is the chip micrograph and performance summary. So this was taped out in 28 nanometer. And we can get a peak performance of about 5 TOPS, tera operations per second, consuming 100 milliwatts, and the peak average system energy efficiency is as high as 437 TOPS per watt. So some detailed results are, this is the IMC measurements and variability. So you can see that there are some variability in the x-axis is the MAC value and the y-axis is the output. So for the same MAC value, there are some variability. Some will be, for example, here +1 and 0, for example. But this is for the single macro. But even if we look at the total 108 macros, we can see that there's small macro to macro variation. The RMS error didn't increase that much. So these have been verified by measurements of these 2D histograms when we just measured a lot of these thousands of random input vectors for all the columns, and we generated the partial MAC value, and red box basically highlight the ideal value, and you can see some of them go outside of that, creating some variability. If you look into the chip power breakdown, we can see that the PE clusters dominate the power consumption, and among the PE cluster power, the IMC SRAM macros power dominate the power overall PE power consumption. So this is good. Obviously, we wanted to evaluate the overall system power and energy. We want the parts that actually do the computation and storage dominate the power instead of other peripheral or controlling parts. And these are the energy efficiency TOPS per watt results for different precision and different networks. You can see that the single macro level energy efficiency is obviously going to be higher than system level when we include like 108 macros and all of the other controllers and activation memory and SIMD and so on. So you can see that the peak system level energy efficiency is not too far off from the macro level energy efficiency. And obviously, if we average out the overall energy efficiency when we run the whole VGG9 Resident 18 networks, the average energy efficiency will be lower than the peak. But still, for the system level energy efficiency for the binary, we're getting hundreds of TOPS per watt, which are high numbers. So if we compare our work with some other works that I mentioned on the IMC system, they have been integrating a pretty large memory bits for in-memory computing. As you can see here, we're one of the largest ones. But I think one thing to highlight is that we're getting the highest system level peak and average energy efficiency. And compared to one of the works by Princeton, we're still getting noticeable reduction in the energy per inference for the same VGG9 network in terms of how much energy is consumed for the whole inference of this network in terms of microjoule. Okay, so let me quickly go through these other works that we're doing going beyond the single IMC macro design. So in this second work that has been presented earlier this year, this is called Modeling and Optimization of SRAM-based in-memory computing hardware design. So in this work, as I said, there are a number of different design parameters that we need to carefully optimize. For example, how many rows are we going to turn on? What's the ADC precision? And there are also non-ideal effects, such as how much variation is there in the capacitor and the transistor, and how much ADC offset is there? What's the variability? So regarding all these different, under different noise and variability, we want to optimize the best core set of design parameters. And we put together this Python-based framework that we open sourced in this GitHub link. And we can do design space exploration we can change the quantization range in the clip linear quantization. And depending on what are the offsets and different noise, we can see what are the achievable CFAR10 accuracy. And if we compare these to the C3 SRAM chip results, it's a little more conservative, but still pretty close to the actual measurement-based results. So this validates the effectiveness of the model. In the third work, this is the IMC noise-aware training algorithm. So this is under revision for IEEE design and test, and the title is Realizing Hardware Noise-Aware DNNs by IMC Noise Injection. So as I said, there are certain noise and variability associated with these analog IMCs, as you can see here in our own work. from other works from CICC 2020 and JC 2020, you can see these non-ideal factors is not a straight line. There are some ranges of outputs, ADC outputs, for example, for the same mathematical results. So the prototype chip measurements show variability, right? And especially when we turn on more number of rows, and also in some higher noise situations where the VDD is low, for example, there could be significant accuracy loss. So some works try to combat that by limiting the number of rows we turn on at the same time to improve the SNR. For example, in the National Tsinghua University's work, they only turn on 18 rows, for example, but this approach will reduce the parallelism amount and achievable energy efficiency. So, and there has been a number of works where they try to incorporate some of the hardware characteristics or different types of noise during the training, and then so that during the inference, the accuracy could be improved. So there has been some works, for example, by UIUC, that they actually have some training circuits for IMC, but this incurs a large overhead in area energy. TSMC, in their work, they put together a non-linearity aware training. They're moving, their RBL is being driven down by how many transistors are turned on, and there's inevitable non-linearity depending on the voltage range. So when the multiplication result is high, they try to put together this nonlinear factor during the training process. There can be some quantization aware training, but they didn't quite get satisfiable accuracy improvement. And in a recent Nature Communication paper, there has been noise injection training. This one primarily focused on phase change memory. And they injected Gaussian noise for individual weights in the PCM. However, some of the crossbar or subarray structure and the ADC quantization have not been considered. So in this work, the first observation we found out is that predominant amount of works, as I showed in the previous slide, actually try to inject some Gaussian noise that they try to characterize from individual cells or weights. However, you can see that the Gaussian fit doesn't really, cannot really satisfy a lot of different scenarios that will happen depending on different MAC values, and typically there's a finite concentrated range, as I mentioned previously. So in the towards the maximum and minimum, there's not going to be much noise at all. It's all going to be just, highest value or VDD or zero. In the middle, there are these noises. So there are definitely some hardware dependent noise. So that's what we try to do, that we try to understand that the amount of error depends on the MAC value, depends on the hardware, and the DNNs trained with Gaussian noise results in suboptimal accuracy for the actual IMC chip when we apply some of these previous algorithms onto our IMC chip measurements. So we propose to inject the noise actually based on hardware measurements, and we can do that because we had these two different IMC SRAM prototypes, right? So we try to improve the DNN accuracy and basically recover, hopefully, majority of the accuracy that has been lost. And this can be done by considering the crossbar and subarray structure and understanding that this range is there, quantization range is there, and considering that, we train it so that it can behave much better when we do the inference. So this is based on the XNOR SRAM IMC noise measurements, and we try to evaluate different networks, different precisions, and different supply voltages. And we also try to do the same thing for the C3 SRAM IMC chip measurement noise. I think the key takeaway is that for pretty much all scenarios, we can get some noticeable amount of improvement using the proposed noise-aware IMC inference, which is in the yellow line. But noticeably, when the noise itself is higher, we can actually get more improvement and get quite closer to the baseline, although there will be some amount of degradation when the noise is really high. But obviously, we can get significant improvement compared to the conventional inference when we didn't do any of these noise injection training. And finally, I would like to go through this final adversarial robustness work. So this will be presented in DAC later this year, and we're trying to leverage the noise and aggressive quantization of IMC works towards adversarial robustness. So there has been some of these adversarial input attacks. So you just apply a little bit of noise and the networks will be confused, or you can just flip a small number of bits and you can see that like these resonant accuracy will dive down to almost zero. So to combat these, there has been some algorithm work, some hardware works. However, some summarized drawback is that they try to basically inject some of these noise during the training process to improve these, but the noise is not really specific to the actual hardware. For example, if your hardware is IMC and there's no quantization or partial sums at the crossbar level, again, if your hardware is like that, and they primarily use synthetic or Gaussian noise to inject during the training process, or they can exhibit some redundancy overhead. So in our proposed work, we also try to inject IMC noise that we actually measured from prototype chips of the X4 SRAM and C3 SRAM, and we inject these during DNN training and try to evaluate whether this can help actually on the adversarial robustness. And actually, we found out that whether we do non-adversarial training or we do some adversarial training such as PGD, in all cases, we found out that when we do the IMC noise-aware training, then the inference accuracy or the accuracy against these PGD attacks improve by a couple percent up to close to 10% across these different precisions, 1-bit, 2-bit, 4-bit of resident 18 network. So in summary, today I started from presenting the single IMC SRAM macro designs, including others. We prototyped resistive and capacitive SRAM IMCs. Many single IMC macros have been presented in recent years, demonstrating hundreds or even recently thousands of TOPS per watt. And our IMC prototypes, XNOR SRAM and C3 SRAM chips have been characterized extensively. And going beyond the single IMC macro designs, first I talked about our PIM-cut chip that integrated 108 IMC macros. It's programmable with custom ISA and it has the specific hardware loop support. And we demonstrated high system level energy efficiency. We also published a modeling and optimization framework that can optimize core design parameters. And we try to improve some of these accuracy degradation by training with IMC hardware noise. And we demonstrated better accuracy than Gaussian noise injecting counterparts, especially when the IMC noise is high. And finally, we try to also exploit the IMC noise to achieve more robust adversarial DNNs. Okay, and I want to acknowledge my collaborators, Minggu Seok from Columbia, Dalian Fan from ASU, and all the students who did the majority of these works. And our sponsors include NSF, SRC, the Seabrook Center, which is part of SRC and DARPA. And we have also been funded and collaborating with Samsung Advanced Institute of Technology. So that's it. Thank you very much for your attention, and I'll be happy to answer any questions.
네, 질문 있으시면 해주시면 감사하겠습니다. 제가 먼저 질문 드리면요.
네네.
정확하게 제가 잘 이해를 못한 부분이 있는 것 같은데, 예를 들어서 그러니까 SRAM 전체 인메모리 컴퓨팅 할 수 있는 전체 시스템 안에 못 들어오는 사이즈의 딥러닝 모델 같은 게 있다고, 뭐 극단적으로 예를 들어서 엄청나게 큰 사이즈의 매트릭스 벡터 멀티플리케이션 같은 거를 해야 된다고 하면 그게 지금 D램에서 어떻게 이 엑셀러레이터로 패치가 되는 건가요?
네, 그러니까 결국 당연히 뭐 모델 사이즈들은 계속 커지고 있어서 이제 실제 상용화 칩 그리고 뭐 결국 D램과 리얼타임 커뮤니케이션 하려면 이제 결국 엑셀러레이터 칩에서 뭐 D램 간의 인터페이스가 있어가지고 그거를 리얼타임으로 들여오거나 아니면 뭐 뭐 다른 브릿지를 통하거나 결국 그런 인터페이스가 필요하고요. 근데 이제 좀 이제 아카데미아 레벨에서는 사실 그런 DM 인터페이스를 리얼타임으로 구현하려면은 일단 온칩 DMA 컨트롤러가 있어야 되고 여러 가지 IP도 문제가 있고 그렇기 때문에 사실 저희 그룹에서 이 다른 IMC 말고 다른 칩에 좀 D램을 이 직접 디지털 엑셀러레이터 업색할 수 있는 그런 모듈을 설계하기도 했었는데 어쨌든 그게 어떻게 보면 좀 만만한 게 아니어서 일단 이런 프로토타입 칩 레벨에서는 어쨌든 D램의 웨이트들을 뭐 스캔 체인 같은 걸 통해서 일단 이런 액티베이션 메모리나 이 IMC 매크로에 라이트 할 수 있는 그 펑셔널리티가 서포트가 되는데 그런 게 이제 뭐 리얼 타임으로 되기보다는 일단 어떻게든 이제 잠시 동작을 멈추고 이것들을 다시 새로 라이트 하든가 그런 것들은 서포트가 되는 거죠. 근데 결국 상용화 칩에 가서 뭐 전체 보드 레벨에서 D램이 있고 이거랑 이제 통신을 하려면 그런 D램 인터페이스가 따로 서포트가 돼야겠죠.
아, 네, 알겠습니다. 그리고 그 하드웨어 노이즈 모델 그 세 번째
네네.
그 프레젠테이션이었어.
네네.
거기에 그러니까 원래 가우시안 노이즈 사람들이 이제 좀 더 그 노이즈에 강인한 거 만들려고 방금 여기에서 그 가우시안 노이즈가 이제 그 실제 하드웨어 노이즈를 제대로 모델링 못하니까 지금 실제 하드웨어에서 그 메저한 거를 바탕으로 그거를 사용을 해가지고 지금 트레이닝을 다시 한 거인가요, 이게?
네, 그렇다고 볼 수 있습니다. 그리고 한 가지 다른 점은 결국 이제 뭐 예를 들어 뭐 SRAM이든 아니면 이런 NVM이든 간에 뭐 그 노이즈의 어쨌든 이런 뭐 디바이스의 좀 특성을 파악해 가지고 예를 들어 보통은 이런 웨이트에 인디비주얼하게 이 웨이트에는 뭐 웨이트 값이 모일 때 얼마만큼 가우시안 노이스를 주고 뭐 이런 그 웍들이 보통 있었는데 근데 이제 저희가 생각하는 제일 큰 좀 디스크레펀시는 어쨌든 노이즈라는 게 이제 인디비주얼 셀에서도 당연히 발생할 수가 있는데 그것들이 결국 이제 어큐뮬레이션 하면서 리드 빗라인에 함께 모아지고 그게 또 이제 ADC를 통과하거든요. 그러니까 결국 그런 두 가지, 세 가지의 노이즈 소스들이 다 결합돼서 결국에는 이제 디지타이즈 된 다음에는 이제 뭐 노이즈가 없다고 할 수 있으니까 그러니까 결국 이 ADC까지 통과한 다음에 라는 말은 결국 이게 웨이트당 노이즈가 다른 게 아니라 어떻게 보면 이제 맥 밸류당 결국 그거에 따라서 노이즈가 달라지고 그게 어느 밸류에 따라 이게 여기서 보시듯이 확 달라지고 또 뭐 그런 것들을 이런 다른 방식으로 보면은 좀 완벽하게 소화를 못하기 때문에 결국 이런 맥 기반으로 노이즈를 저희가 칩 메저먼트 기반으로 해서 좀 특성을 캐릭터라이즈 해서 결국 뭐 이제 실제 이걸 트레이닝 할 때 당연히 뭐 1000개 뭐 1000 인풋 맥이라고 하면은 보통은 트레이닝 할 때 그냥 뭐 GPU나 이런 것들이 뭐 1000 인풋 맥을 그냥 샥 다 계산을 해버릴 텐데 여기서는 이제 저희는 트레이닝이 좀 느려지지만 어쨌든 그거를 뭐 만약에 IMC 저희가 생각하는 게 256 로다. 그래서 그게 226 인풋의 맥을 한다고 하면 그냥 이 트레이닝 할 때도 뭐 포워드 패스를 건널 때 그거를 1000개를 256개로 쪼개서 결국 그 256개의 맥 밸류, 컬처선 밸류가 뭔가에 따라서 그거에 해당하는 노이즈를 인젝트해서 트레이닝하고 그럼 결국 이제 인퍼런스 할 때도 그거랑 제일 비슷하게 될 테니까 그런 방식으로 해서 좀 애큐러시를 이제 똑같은 아니면 비슷한 칩에서 인퍼런스 할 때 더 좋아지게 할 수 있도록 하는 거죠. 애큐러시가.
그리고 한 가지 더 질문이 있는데요. 이게 지금
네네.
트레이닝 할 때도 이게 사용을 할 수 있을 것 같기는 한데 그 보통 이제 트레이닝 할 때는 뭐 이제 배치 사이즈를 일부러 키워가지고 컨벤셔널한 하드웨어에서는 이제 좀 그 최대한 데이터를 리유스 많이 하려고 하는 방향으로 하는 거잖아요. 근데
네네.
여기에서도 그런 식으로 비슷한 스킴을 적용할 수 있는 건가요? SRAM-based in-memory computing에서도?
인퍼런스 할 때요?
아니요. 트레이닝 할 때. 예를
트레이닝 할 때요?
들어 그러니까 배치 사이즈를 일부러 늘려가지고 예를 들어
근데 일단 뭐 한 가지 클래리파이 할 거는 어쨌든 트레이닝 자체는 이제 IMC 하드웨어에서 일어나는 게 아니라 이제 그냥 저희도 GPU에서 돌리는 거고요. 근데
네,
뭐 GPU에서 그쵸. 뭐 사실 트레이닝 자체는 배치로 이루어지는 게 맞죠. 보통 다 배치 노멀라이제이션 레이어가 들어가고 그런 것들을 쓰기 때문에 뭐 배치 사이즈 뭐 굉장히 낮게 하면은 사실 트레이닝 애큐러시가 잘 안 나와서 보통 뭐 작게는 막 뭐 64, 뭐 128, 더 크게는 훨씬 더 크게 가져가기도 하고 그래도 어쨌든 뭐 인퍼런스 때는 뭐 배치 사이즈 1으로 한다든가 더 작게 해도 되는데 어쨌든 큰 배치로 트레이닝 할 때도 어쨌든 이런 거를 저희가 지금 하고 있는 거죠.
네, 감사합니다. 혹시 다른 질문 있으신가요? 네, 다른 질문 없으시면 네, 훌륭한 톡 준비해 주신 서재선 교수님께 다시 한번 감사드리고요.
네네, 감사합니다.
감사합니다. 네, 다음에 정식으로 다시 인사드릴 수 있도록 하겠습니다.
네, 감사합니다.
네.